Yes, welcome back, Form Force. Today we are going to look at, still we are dealing with rates of reactions, and we are trying to analyze, to learn how to use graphical data or how to answer questions which are based on graphical problems. So like today, we have still on measuring the rate of loss of gaseous products, the rate at which the mass reduces due to loss of gases. That is, we are trying to understand how to measure the rate of a chemical reaction based on the rate of change of the reactants based on the loss in mass. And this loss in mass, we said, is due to the production of gases which escapes into the atmosphere. So let us look at this question. The table below shows the results for the reaction between bromine and methanoic acid carried out at 40 degrees Celsius. So the reaction was carried out at 40 degrees Celsius. 40 degrees Celsius. And it is the reaction between bromine and methanoic acid. So these are the results. These are the results. These are the results. So we have time. When time was at the beginning, the concentration of bromine was 0.1. Then the concentration changed from 0.01 to 0.02. So we have change in concentration and the time taken. Change in concentration and the time taken. Now, this third column is just the same as the second column, but to make us draw a graph. Drawing a graph using these figures directly is cumbersome. So we have decided to convert these numbers into whole numbers, but to power 10 to power 3. Like if you are given figures like this one, like in our case, if you have at time 0, we say this is time in seconds, then we have concentration of bromine. Now, we have 0.001, that is 0.0100. Then we have, at 30, we have 0.000. At 60, we have 0.00. 0.0081. At 90, we have 0.0073. And the last one, which is 600 seconds, we have 0.0013. This is 7. So what can you note? As the concentration decreases, the time also increases. Meaning when the concentration is low, the reaction proceeds at a slower pace, and therefore the time taken will be longer. It takes longer for the reaction to be complete when the concentration is low. It takes a shorter time for the reaction to be complete when the concentration is high. But now we have a third column which we have created. This third column is concentration but times 10 to power negative 3. Now, how have we come up with this negative 3? If you want to convert these figures into whole numbers, then don't use the largest. Go for the smallest and convert the smallest into a whole number. So it will be 1, 2, 3, 4. So it should be negative 4, not negative 3. That is, correct that. So this one should be 10 to negative 4. So that is printing error. Make sure that you correct that printing error in your notes. So we have 1, 2, 3, 1, 2, 3, 4. So this one will give us 13 times 10 to power negative 4. This one will be 1, 2, 3, 4. We have 73 times 10 to negative 4. 1, 2, 3, 4. 81 times 10 to power negative 4. 1, 2, 3, 4. 90 times 10 to power negative 4. 1, 2, 3, 4. 100 times 10 to power negative 4. So when we'll be drawing the graph, we simply plot a graph using our whole numbers. Then we raise them to power 4. Now, we move on. So that is our data. And it goes on like that. So make sure you calculate that up to the end. To power 10 to power negative 4 times 10 to power negative 4. Then the first question we are asked, plot the graph of concentration of bromine against time. So we are told to plot the graph. We are told to plot the graph of concentration of bromine against time. Now, if you want to plot the time, we'll have y-axis and then x. So we are told concentration of bromine and concentration in moles per dm cubed. And these values are times 10 raised to power negative 4. Times 10 raised to power negative 4. Then down here, you'll have time. Time in seconds. Time in seconds. Then you look for an appropriate graph. So how will that graph look like? That graph will look like what we have here. Look, so you should zoom it properly. Will look like what we have here. So here we have concentration of bromine in moles per decimeters cubic, but times 10 raised to power negative 4, because all these values are times 10 raised to power negative 4. Then on the x-axis, we have the time. The time is in seconds. The time is in seconds. Then we plot. After plotting, you have your curve. So you can see the shape of that curve. You can see the shape of this curve. That when the concentration is when the concentration is 0.0100, the time taken is very short. When the concentration is around 80, not 80, but when the concentration is around 0.0800, you'll find that the time taken is 80 seconds only. As the concentration reduces, the time increases. Because look at a low concentration. Check at a concentration of around 0.008. The time taken is over 560 seconds. So from this graph, we can see that as the concentration decreases, the time taken increases. Why? When you have a low concentration, the particles do not collide more often because they are few. They will take time to collide with each other. And we talked about the collision theory, where we say for reactants to be converted into products, the particles must be colliding. Must be colliding. But if the number of particles are fewer, then the number of collisions will not be high. When you have more particles, due to high concentration, they will collide more often. And when they collide more frequently, if you have high frequency of collision, what happens is that the rate of the reaction will be high. When the rate of reaction will be high, the reaction will take a shorter time to be complete. A shorter time to be complete. So, the higher the concentration, the higher the frequency of collision between the reactant particles, and therefore the higher the rate of reaction. And when rate of reaction is higher, then what happens? The time taken for the reaction to be complete will be much shorter. Let us meet in the second part to complete the equations dealing with this graph.